I should be in the room. That's it. Hello? You are. Echo because I'm in the room here. Okay.
And then we'll give you a point. Bunch of announcements before we get started with our first talk. Welcome to all of you who've come from, many of you, very far away. We're very grateful that you come. I would like to encourage everybody to go get a program if you haven't. Okay, I would also, we have the week's events in here. I would like to also take a moment to thank the people who make the conference possible. First of all, we have organizers. I don't know if you guys have seen Dave Van Biesen, who's around but not in the room at the moment. Amalai Oyaki, waving here. See, these are also people who will help you if you need help during the event. Katie Bechtold from APL, Amalai's from JPL. My name's Alan Unell. I'm from the Aerospace Corporation. I also want to thank the people that really make it possible. Star Dundee, who came all the way from Scotland and have really cool fiber technology. AdaCore, you should go see how to write really safe code. OAR is going to tell you about real-time embedded systems. TT Tech with deterministic Ethernet, and MathWorks so your code looks good and doesn't screw up. I mean that with all due respect. Okay, so I would like a few announcements. Does everybody know where the restrooms are? Men's room is out to my right, ladies' room out to the left, exits on both sides out the building, emergency exits out towards the north. What else is super important? Places for lunch nearby. We have a sandwich shop just to the north of us. Behind me is north. We have the really good Caltech. Have you guys been to the Caltech cafeteria? It is like a really snazzy restaurant. It's good. It's just to the east of us a little ways, the other side of the Beckman Auditorium, the big white building. You just keep walking and say, hey, where's the cafeteria? And someone will take you over there. We have a raffle at the end of every day. This year we're giving away a bunch of little raspberry pies for your enjoyment. Make sure you take a raffle ticket out at the desk outside. Throw one half in, put one half in your pocket. Keep it all week. What else am I missing here? Wait, raising his hand.
Thanks to you guys. Thank you for hosting this.
No, our pleasure.
The videos are all live streamed on YouTube, so you can, if you have colleagues who could not make it here, you can search on YouTube for Flight Software 2016. There's a live link. They can view the stream. There's also a Twitter account too, where with some tweets as well.
Okay. I think the other thing is we have a dinner set up for tomorrow night. It is booked out at 140 people. If more room becomes available and you haven't registered, I'll make an announcement and we'll take more people in. Please don't. Oh, isn't that nice? So, what are you supposed to do? You're supposed to silence your phones. It's good. That's very fortuitous. Okay, with that said, we have a full week. Our first speaker, where's Rhonda Fitz? Do you have any more announcements? Are you done? Are we done? 1, 2, 3, go. Make sure you take those souvenirs that are out there, because you know what? That stuff goes back to my office. That's not good. Okay, Rhonda Fitz, I'm going to get you to your presentation here.
You're on day 2 here.
Am I?
Yeah.
Not good.
We're looking ahead to tomorrow, but
How's that?
there you go.
There you go. Rhonda Fitz, number 1. Okay, here's your presentation. Let's get you a microphone. Do you have a pocket?
I'll just clip it to my waistband.
There is a clip right there. Okay. And there's the pointer, and it's on. Thank you.
Is this turned on? Is it on? No? Alan, did you not turn it on?
Hold on. Is the green light on?
There it is.
It is now.
Ooh, loud. This on so it doesn't fall off, maybe. Good morning, everybody. Rhonda Fitz with the NASA IVMV program here from West Virginia. That's a picture of our facility there, the 2 buildings, the pink lower one, and then the towers off the north tower on the right-hand side. It's good to be here. Thank you. There's a handful of people here too from IVMV as well. So hope you guys are familiar with the IVMV program. If not, please do come and by and talk to us. I won't go into a whole lot of background about our program, but if you aren't familiar with NASA IVMV, please do come and talk to one of us. So I'm going to jump right in to fault management, which is my passion. It's part of flight software, and it's to me I think it's the most important part, of course. The advantage working at IVMV program is that we see a lot of different missions. We get to see across the agency a lot of the different projects that are going on. A lot of variety. Class A software, highly critical, safety critical, mission critical. Looking specifically at fault management architectures, we look at the different mission types. And we discovered there's a huge variety in approaches, in the designs, even in terminology, even across the same mission domains. These are truths here. As the complexity of a mission increases, so does the fault management complexity. Some of these statements are pretty obvious. There's a lot of distribution that's being done with the fault management in the software. Highly complex missions obviously need to distribute a lot of that software that takes care of fault management. Documentation as well. You don't oftentimes pick up a fault management document. It's usually embedded within all the other software documentation throughout the system. So gaining that understanding of how, in fact, the flight software is tackling fault management is a big endeavor. You really need a great system understanding of the project. We're looking at capability assessment. When IVMB assesses a project or a program, we do it from a capability-based analysis perspective. Used to be a lot of artifacts-based analysis, but now we're leaning a lot more towards adaptive IVMB and looking more to the mission capabilities themselves. We want to improve software assurance, not just IVMB, but software assurance across the board, safety and mission assurance. That's the goal. And our research here, we're into the third year, funded by the Office of Safety and Mission Assurance out of headquarters. They have a software assurance research program called SARP, and this initiative has been funded called Fault Management Architectures. I'll have a little bit of redundancy in my talk today because I go through the fiscal year 15, 16, and then the current work that I'm doing. Try to just kind of get you guys up to speed on what's been going on. So here are 4 main challenges that from my perspective anyway, when we're talking fault management. We've got increasing complexity. Hardware fault protection, we're talking a lot more of the program, of the mission is being done with flight software. There's so much more importance being placed on software. We're looking at not just collecting ourselves after something goes wrong, but trying to prevent, trying to anticipate, and then maintaining capability rather than just reacting. We've got these fault management systems are embedded within the software, throughout the software in most cases. And so when you validate your flight software, you have to look at those higher level system capability requirements. It may not be obvious with a more direct approach. You've got to basically keep that entire system functionality in mind. We'll talk a little bit about off-nominal conditions, how challenging they are to identify, how we can get our hands wrapped around these ideas of what might possibly happen in our mission. Of course, obviously, we're going to follow the risk. We need to mitigate that risk. We need to anticipate. We need to prevent things going wrong with our mission in order to provide assurance. And of course, we're always trying to improve our assurance, our level of assurance. We need to make sure we're providing the rigor that's needed for our software systems. So this is an overview of our initiative. We had goals to look basically at architectures that were set up for fault management, investigate what kinds of methods or assurance strategies are used here at the program, and a lot of that is tied into the visibility. So these were the 3 main thrusts that we started off in FY15. These are the lists of the different missions that we had purview to. Now, it wasn't just me. I have to give a shout out to Jarek Whitman, to Ryan Stickway, and to an entire fault management community of interest at the NASA IVMB program that has really been involved in each of these missions in depth. A lot of what goes on with fault management is understanding the system itself, understanding what the flight software does, how it's architected. We started off with a survey of different questions. So a lot of what we did establishing a technical reference was in the journey. The benefit was in the journey because there were a lot of questions that had to be figured out with the system itself. And you see the different mission types there. Launch vehicles, we just tackled this past fiscal year. But you would think that there would be a lot of similarity across the mission domains, but instead we didn't see that very much. You have a different project, you have a different fault management system. So the early goals, we were looking into what kinds of architectures, obviously, but how do you provide assurance? You strategize, you come up with a design on what you want to say. How do you want to say it at a KDP, at a milestone review? What is it that you want to assure that works? And then you work backwards from there. You want to say, how do we come up with the evidence to provide that assurance? Visibility is a very interesting topic because a lot of times we're working remotely, we're independent, we're not working right next to the developers. So we rely on artifacts, we rely on different documents, different software pieces and parts that the developers will give us. We don't always have access to their simulators or to all their code. So it's been a challenge to try and figure out, okay, with what do we start with? If we have a fault tree, if we have a FMEA, if we have just a design documentation, what do we do with that? How do we provide assurance that will ensure that mission will succeed? And of course, as part of any research is the dissemination of those results. So beyond this attack, basically with this study, is being able to share the knowledge that we've garnered with all of our in-depth study. To setting up this technical reference suite, it's a common term, I believe, across NASA that you want to have something to go back on to look at what your results were and to make some conclusions on your own when you for like a heritage analysis. So bringing together all this information, we were able to establish this technical reference suite, which was part architecture focus with a lot of details on whether it's distributed or a centralized architecture, how the different layers work, how the different tiers, then specific assurance strategies that we were able to provide, and tying them into our technical framework. What part of the life cycle are we going to say what? What kind of assurance can we provide if we're in the requirements phase, or if we're actually all the way back in testing? And what can we do if we have difficulty with the visibility, that a program or a project is not giving us a lot of insight into their program? What can we do? What are some of the IVMV methods or techniques can we basically uncover more of the details that we need? And there's a bullet there on an adverse condition database. I'll talk a little bit more about adverse conditions and establishing this repository of, hey, these are some off-nominal situations that some projects have come across. These are common for certain domains, maybe, or certain types of missions. And it's almost like a SME in a database. We need an expert to be able to give us some insight so that when we have newer, younger analysts coming in, they've got some place to start. We're not just going to rely on what the project tells us, what are the adverse conditions that they expect to face. We want to add value by coming up with our own and being able to say, hey, wait, did you think of this? We've seen this in another mission that's similar, or we've seen this on a certain component that you're using and another project. So we're bringing together more of that information. And again, this was the second year of the initiative. We worked on bringing together that tech reference suite and giving it a better user interface. We have it populated on Confluence so that it has easier accessibility. Organized the assurance strategy grouping. We're trying to keep that as a dynamic collection of assurance statements because we are, like I said, we're very adaptive with our IVMV. So as projects and things change, those assurance statements are maturing as well. So in this research, there's 3 thrusts. These technical reference products basically are improving on those, getting them out to the point where our analysts can use it and the SNMA, other agents can utilize this information. So here's just a screenshot of a technical reference title page where we have the, I think there's a pointer in here. The architecture matrix would be on the top, then the assurance strategy reference, and then lastly the visibility matrix. And each of these are linked here all in one place where it's easy for anyone to assess. And for example, you jump into an architecture matrix and you go into lots and lots of detail. So there's everything and anything you could want to know about these specific missions as we gain from our community of interest. So basically that's what we accomplished is improving, expanding on those for ease of sharing the information. Second part was the adverse condition database. We started as a prototype. As a matter of fact, I worked with a couple of summer interns to put this together initially, and then we've expanded. We're populating it with the different projects, and everyone comes at it from a different perspective. Again, we don't have a common workflow established yet, which is part of my initiative for this year. Is every project kind of, you start off with what the project will give you, but you want to go beyond that. So we want to develop more easier access and more efficient use of this database and give it a user guide, basically, so everyone can come in and we're all focused on the same terminology. So I gave a quick definition of what we're calling adverse conditions. Subset of off-nominal. Basically, you're preventing a return to nominal operations unless you do something, right? So it all ties into fault management architecture, because how you have your flight software architected will determine how you'll be able to react to these adverse conditions. So down here, it's a cool picture. We've had lots of academic discussion on how do you categorize your adverse conditions. Are they the same, or are they different from hazardous or anomalous? And so these conditions are all flowed up. You've got basically a condition that you're facing within a certain behavior within a scenario of a specific mission. So you can see how it all depends on this tree here. In order to make sure we were not just throwing together a bunch of adverse conditions that and saying, oh, we're great, we've put up this list, right? We took from some Agile Scrum methodologies and threw together a user story workshop. And we got stakeholders together in a room, talked about, hey, why do we care about adverse conditions? What do we want to do with them? What do we consider adverse conditions, and how is it important to us and to the work we're doing here? So we went through this process. Now, I'm talking a little bit about Q3 for those of you not familiar. Q1 basically is the nominal case, is the software doing what it's supposed to do. Q2 is the software not doing what it's not supposed to do, those unexpected things. And then Q3 is how is the software reacting in an adverse condition. So the Q3 is really where a lot of our emphasis is being placed for the adverse condition database and for this fault management. So to architect this database, it's not just a flat list. We have lots of, sorry if you can't read that very well, but I can give you a copy if you need one. You've got interrelationships between faults, between failures, hazards, anomalies even. You've got a lot of data tied in with your mission, with your component, and all of that is structured with a database with different relationships, many to many cases. So this was put together over the course of a year and based on a lot of that user story workshop that we went through. Here's a screenshot of a couple screenshots I'll show you here. This is the opening, kind of a generic listing. You've got projects, you've got AC identifiers, names, domains, hazard types, different types of, and we're incorporating all this within our enterprise architecture at the IVMV program with the help of our software assurance team. They're in the process of doing that now. A couple more screenshots, how we talk about these adverse conditions are related to a specific mission. And within this database, it's all in one place. We have the mission, a couple of mission details in there, and then generic domain lists, hazard lists, fault lists. And we can tie in with other databases so we don't have to duplicate the efforts, because there are a lot of different hazard databases that are already out there. So we've got the hooks in place for that. And like I said earlier, we're geared more toward capability-based assessment. So we want to make sure that we've got those capabilities of the mission defined, so that if you have a similar capability on your project, then you want to go and follow that capability, make sure you're addressing it. So this database has been refined and productized so that we have that insight into the off-nominal mission capabilities. And the third part would be then to pass around the information to kind of disseminate it. That's part of what I'm doing here today as well. I've been to the Space Symposium, the 31st and the 32nd Space Symposium, give presentations, and there's detailed papers also out on the NEN, if you're familiar with that, or if you need access, you can just contact me as well. So we hope to share that with other folks within the fault management community and with the software assurance community itself. So this is kind of a, like I said, overview. This gives it a chart to, NASA's always looking to, okay, where's the value? What's the value that's come of this? And we want to make sure that that's clear, that we're promoting that knowledge in order to improve the assurance. We want more rigorous IV&V analysis. And that, in the same sense, when you understand that, then again, from the developer standpoint, you can anticipate, hey, what do I want to do properly? How can I set this up so that when I want to analyze the architecture later, I'm not running into any troubles? So we're really focusing on that fault management, project areas of vulnerability, high risk, so that we can have that reliable and resilient software. So basically, we're noticing, back, I think it was 4 years ago, Flight Software kind of picking up from some work that Lorraine Fesk did with the fault management community of practice, identifying a gap here, a need basically amongst the community that fault management really needs the attention that it wasn't getting. It wasn't being addressed early enough in the life cycle. It wasn't given the emphasis that we as a flight software community believe it really does need. We can't afford to put it off and say, well, we'll tackle the nominal, we'll get to the off-nominal later. Time, budget, right? Well, that's not really acceptable. We really need to address it. And there's no reason why you can't address it at the same time you're talking nominal. It takes, as much effort basically to say, okay, here's how I'm going to put the software into place. Here's where the off-nominal, this is what can go wrong. Let's address it then. So hopefully with this adverse condition database, it will help in that regard to keep you thinking. It's really cool because you're always trying to think evil. You're trying to break it. How much fun is that, right? So you really want to focus, get that focus on the fault management within your software development projects, and you'll basically bring down that risk. Focus on how you're going to mitigate before things go wrong. Have your architecture assessed to make sure that everything is in place so that when trouble arises, you are in a spot where your software can deal with it. We're talking security, information assurance now. You've got vulnerabilities. It's not just accidental anymore. Sometimes it's malicious. So you really need to be able to be thinking about along those terms. Right now we've got our adverse condition database basically has current projects and current adverse conditions that we're trying to expand on. We're going to set up a pseudo project of security, and we're going to come through with all the CWEs that are recently released, and they're updated, and incorporate those into a project as well, so that we have this place where we can double check and make sure we're covering the assurance that we need. So like I said, the additional information, some papers that I've written on the NEN, anything about the software assurance research program is up there as well, and there's my contact information. And I welcome any questions or any comments or any collaborations as well. So, how'd I do on time, Alan?
You did great.
Okay, good.
Questions? Okay, thank you very much.
Sure.
Okay, let's see. Our next speaker is Eddie Benowitz from JPL. If you're comfortable with that, that would be great. Are you okay with this?
Yeah.
Great. laser pointer. Front and back, and the laser.
Thanks, Alan. Welcome, everyone. Today we're going to talk about our new Mars mission, the Mars 2020 rover, and some ideas we had for doing onboard scheduling. So we'll give you a little introduction, and basically we're going to take a top-down tour of some ideas we had kind of at a system level. This is very early, but we're going to walk through what we want to do on board as far as autonomy for this mission. And I want to give a big thank you to, this is a team effort on these ideas. Stephen Kuhn's our system engineer, and he's come up with a lot of this and negotiated together. Also a huge thanks to Steve Chen, who's here. They have a tremendous amount of experience, and his wisdom and inputs have been really valued. And also to his whole team, especially Greg Rabideau. He's actually joining our software development team, and he brings with him quite a bit of experience as well. So thanks to all of those folks. So this is the Mars 2020 rover. It might look familiar. This is, the body is essentially quite similar to the Curiosity rover, which is on Mars now. It's going to be very similar, new instrument suite. And it has a bit different goals. This one's going to collect core samples from rocks, hopefully leave them on Mars for maybe pick up by a future mission. But it's going to leverage quite a bit from the Curiosity mission, both in terms of hardware and in terms of software. So we have high hopes for a decent amount of reuse and refactoring on the 2020 mission. Let me introduce to you some of the terms I'm going to use in this presentation. A sequence is how we do commanding traditionally. It's a file consisting of essentially time-ordered commands. And on Mars missions, and particularly on Curiosity in 2020, we need to put the rover to sleep at night to recharge the batteries. So it has that sleep-awake cycle, which is a bit unique. Some of the orbiters don't have to deal with that. In addition, before we use an actuator, perhaps we need to heat it up in advance so it's nice and toasty and safe to use. So we will talk about preheating in this presentation. And also we have this term called a parameter, which is essentially a saved value on board the spacecraft. It's really only changeable by the ground. So let me introduce you a little bit to the prior process that was used on the Curiosity rover. Any action, again, was started up by a series of sequences, typically. The ground has to create these sequences maybe every day during the work week, say, or every other day. And the process is quite lengthy, right? To go from data coming down from Mars to actually creating the sequences, analyzing it, testing it, putting it all together, doing safety checks, that can take over 9 hours. Not always, but sometimes. Also, due to uncertainty in terms of how long a particular sequence might run, or just the onboard behavior, margin has to be inserted into these sequences, and that does result in some cases, wasted time, wasted onboard energy. Also, because the ground has to be in the loop for this sequencing, you really can't take advantage of the onboard knowledge. Suppose a sequence finished early, right? We might take advantage of that extra time again. So that's another something we would like to improve upon. And also the operation team just has to manage sleep activities and preheat activities. Now there are tools on the ground to assist with this, but again, that is still part of the process that has to be taken care of on the ground. So we wanted to do some improvements for the mission, the 2020 mission. Several goals. One is to improve operations efficiency. If we can run more activities on board, that's a great help. Get more science done. We can have less wasted less wasted resources in terms of time and energy. And another driving factor is instead of taking 9 hours, we want to enable the ground team to be able to generate their uplink products within 5 hours, right? And if you have a shorter time to create these products, that allows you to get more done on board more often, have more useful days of rover productivity. And so to accomplish that, the vision is that we have this onboard piece of software. It's called the onboard planner. It's really more of a scheduler, though. And what is our goals for it is to run more activities when more power is available, start activities sooner if the current activity finishes early, and also onboard manage the sleep cycle. Have onboard the rover decide when to go to sleep. And I should let you know this is very early work. We're just starting the prototype. We're just getting early versions of sort of essentially systems desirements. So what I wanted to do is kind of share with you where we are now. Top-down approach at a high level, sort of giving you a vision of where we want to go, what are the basic capabilities, what does the ground need to tell the spacecraft, and just kind of give you some ideas on the architecture. So we're not going to be talking about implementation today. So at a high level, what does the planner do? The planner is going to be responsible for scheduling all the onboard execution on the surface of Mars. So to take you through that, it all starts with the operations team, and they're going to create a plan file using ground tools, various techniques, and that file is then going to get uploaded to the onboard planner on the spacecraft. And what the onboard planner is going to do, first of all, it needs to make predictions into the future about the state of the spacecraft as far as various resources, for example, power or data volume. You can think of others. We'll talk about others. And once it makes that prediction, given the knowledge of what constraints there are, what resources are going to be consumed by various activities, and a lot of that comes from the ground. Oops, sorry. A lot of that comes from the ground. Based on all those inputs, both the ground plan file and predictions, it's going to generate a schedule on what activities can run when. And this is the onboard portion right here. And in doing so, it's got to, as I said, make predictions and check for conflicts. Okay, so the plan is contained a plan file that is what is uplinked from the ground. And so what we're going to do is we're going to decompose what is in the plan file into various capabilities and data and kind of break it up. So that's going to be the rest of this presentation. It's starting at the high level. What is a plan? What is inside a plan? And how do we use that information on board? Okay, so as I said at the top level, the plan file is what is uplinked from the ground. Inside the plan are activities. So an activity is the lowest level that the scheduler is going to look at. So it's something that can get moved around and executed at a certain point in time. It's that level of granularity. So that's an activity. And as I go through the presentation, we're going to talk about the various types of activities. We're going to talk about various constraints on activities. So we'll go through that in detail as we walk through it. Now, I should also define the term handover. Handover is a point in time when we move from one plan to another. And that's very common in rover operations. In the past, it was, say the rover has a wake-sleep cycle for one day, and then at the end of the day, it's going to hand over and start executing the next day. So it's sort of handing over from one day to the next what the rover is going to do. Okay, and that's a specific point in time. Now, what we have is certain goals that must be achieved at that point in time that we hand over to the next day. So for example, we want to provide the next day with a minimum state of charge so they have enough energy to do their rover activities. So that's sort of one goal. Additionally, we only want to generate a certain amount of data within, say, one day. So that's another data that the ground provides is a limit on how much data we will allow to be collected. We have an end time, and we also have the name of the next plan file. So you can kind of chain them together one after the other. Okay. We're going to walk through this in a bit more detail, but I wanted to start giving you sort of the UML big picture of what we have. So at the top is the plan. It consists of a bunch of activities, and the activity itself contains a bunch of constraints. And we'll walk through this in greater detail as we go. Okay, so you got the big picture. Now I'm going to look at activities. There are various types of activities. Some of them behave different from each other. We're going to walk through that. So as I said before, the activity is the item that is scheduled. It has a type. We're going to go over the types. Each activity has a unique ID across the mission, and that'll come down to telemetry, and it'll make it easier for us to understand what's happening on board. Each activity is going to kick off a sequence, so that's leveraging the legacy system for actually doing the low-level command execution. Each activity has a priority, and we'll use that to categorize activities as mandatory once they're intended to execute for sure, and optional activities are ones that are sort of nice to have. Execute it if you have more resources available. That's kind of the high-level intent. Okay, so activity types. The most common would be just your generic activity. It runs a sequence, and it has a fixed duration, and that would be the vast majority of what activities we use. And then we have some more specialized ones. An expanding activity is essentially the same as generic activity, but it does not have a fixed duration. It can potentially grow in how long it executes. One typical example would be a drive, right? We might say, go ahead and drive until we run out of meet the power constraints, say. And we don't know how long that's going to be, but just keep going. And so that's a use for an expanding type activity. Now, there are a case, say for an instrument, where they have an activity that's very resource intensive. And if it so happens that we don't have enough resources on board to execute it, we'd like to do a backup plan. We'd like to do something similar but less, that consumes less resources. The key constraint is we don't want to execute both of them. You want to do at most one of activities on a list. And so that's where these single selection groups come in. You just choose one from the list, one that fits. But you cannot run more than one on this list. So that's the intent there. For the stay awake activity, that's just a way for the ground to force the planner to make the spacecraft be awake for a certain period of time. Because as you remember, the planner can autonomously generate sleeps. So it's just an enforcement. The ground taking some more control back in a way. We also have several types of shutdown-related activities. As I mentioned before, the planner can autonomously generate shutdowns. And we also have the capability to have manually described shutdowns on the ground. Now, because we are tracking resources, there are different sets of resources that are consumed sort of during the different phases. So when we're actually sleeping, there's one set of resources consumed. During the actual shutdown, right, the various resources consumed would be different. Here we'd be gaining energy, here we'd be losing energy. Similar for as we're waking up, we're actually going to model the energy and data volume that it takes to actually wake up, come out of the sleep. So that's how we break it up as far as those activities. We also have the notion of comm windows. These are periods of time during which the rover is going to be communicating with Earth. And so those are sort of a special case. We have onboard software that already manages that. And so the planner is going to need to be aware of the comm windows and sort of manage its schedule around them. And so that's something that we explicitly need to take care Okay, so those are the types of activities. Now we're going to look at attributes of activities themselves. So these activities, its duration, how much energy it's going to use, how much peak power it could take up potentially, how much data volume it's going to generate, the number of sequences that it could potentially spawn at the same time. Those are all modeled by the ground, and those are uplinked as part of the plan file. And we need that to do our onboard predictions and modeling and check for conflicts. Additionally, we need to tell the scheduler when can an activity possibly run. And we can constrain that. We can give it various constraints on the start time. We can say, let's start between 10 and 11 or between 1 and 2, something like that. So we can have multiple start time ranges. We also have a cutoff time as well. Okay, dependencies. One activity can depend on another. And so we allow expressing that dependency. We can say, B depends on A successfully completing. And we can also check on other status of the activity, whether it's completed, whether it failed, whether it succeeded, whether it was aborted. Okay. So those are dependencies. We also want to constrain parallelism. For example, on a rover, if you're moving the arm around trying to pick up a rock, you probably don't want to be driving around at the same time. That would be a bad thing. So what we want to do is sort of tell the planner not to schedule certain activities in parallel. And the way we're going to express that is just to have a bunch of bits dedicated for each activity. And we'll let the ground define how these bits are used. But basically, if the same bit is set on 2 activities, they're not allowed to run in parallel. The scheduler will make sure that they do not run in parallel, which is what I'm showing here. These 2 activities have the same bit set. And so because of that, this sort of schedule would be forbidden, and this one would be allowed, where they're not running in parallel. We talked about preheating earlier in defining terms. So again, we need to warm up an actuator so it's nice and toasty when we use it. So the way we model this is each activity essentially has a checklist of what thermal zones that it will use. And that's all the ground has to specify. And then we need to do some more work on board. As we place the activity, right, as we put it on the schedule, we have to schedule both the activity as well as the preheat. And also, as is a new sort of requirement for flight software, it's responsible for generating and executing the preheat, monitoring that it's running successfully so that we're at the correct temperature before we run an activity. So that's an interesting new capability. We also have some checks that are done on board against onboard variables. Just some terms, ACM is a saved onboard variable, typically allowing or precluding a particular action. For example, if there's a problem with the wheels, then we're not going to allow a drive. DDI is basically it's something that doesn't persist across a reboot. It's just an onboard variable. And so these can be evaluated and used to determine whether or not we can start a given activity. It's a constraint on the activity, essentially. And at this point, right, because they're onboard values, they're essentially onboard variables, right? We're not exactly able to predict them, so they have to sort of be evaluated as you're sort of dispatching the activity. Okay, so more features. We're going to talk about some of the overall constraints now that you've seen what a plan is, what an activity is, what data is inside activity. Now we're going to talk a little about some features and how we use those constraints to sort of do modeling of predictions in the future. So as far as limiting the data storage, right, we don't want to allow the planner to fill up the whole hard drive, essentially, right? We want to constrain that. And so the way we're doing that is we're going to look at the delta data volume that is generated, right? And so that we know from the ground how much each activity is going to generate. And so basically we have some limit, right? And we check all the activities that we're trying to schedule, and we check that against the limit. Now, there's some distinction between a mandatory activity and an optional activity. We're going to be less conservative on the mandatory activities. Mandatory or in ground intent, they really want them to run. And so we're going to let them go over the data limit. That's okay. Optional activities, which are the nice to have activities, those ones we're not even going to bother scheduling if they would violate the data storage limit. And this is all limits on sort of our flight computer. We're not talking about data stored on the instrument. That's going to be outside of our scope. Okay, now we're going to talk about state of charge. So for each activity, we're going to know how much energy it's going to consume, and we know its duration. And we for activities that are generated on board, like sleeps, for example, we're going to be able to get that same information as well from parameters. And so these are basically the inputs we need. We need how much the activities are going to consume. We need how much is going to get consumed in a quiescent state. And so given that and actual readings from the hardware, we can get out estimates of how much energy is going to be consumed. We can get an onboard estimate of the available capacity, and from that we can predict the state of charge. And so we'll have various constraints on what the state of charge can be, both at the end of the plan and sort of an overall minimum that you don't want to dip your power below. We also have a constraint on sort of the amount of the peak power that can be like a spike at one moment in time where all the activities collude to give you just a worst case spike in power. So we want to avoid that. And so we can track that. There's an attribute that comes from the ground giving us peak power for each activity. And so if we add those all up at a given moment in time, we would know if we exceed a given threshold there. So we have, as I said before, we have our estimate of the current state of charge. We can predict state of charge. So now we want to check that against certain limits. There is one limit against which we will not schedule an activity. That's the soft minimum state of charge. Now, if we're already executing, we can violate this soft limit. It's used to as part of the scheduling. We're scheduling against the soft limit. Now, once you're running, though, there's a second limit that's a bit lower. That would be the hard state of charge limit. And if we find an activity that's actually running, and that actually we have violated the state of charge limit, then we're going to take some action against those activities. So we're starting to get more and more drastic. Additionally, there's a constraint. Again, this one is a looser one that's on the state of charge at the end of the plan at handover. Optional activities, which are the nice to have ones, we're going to check against that. Again, here, mandatory, trying to honor the ground's intent, we're going to let those slide even if they would violate the state of charge at the end of the plan. Okay, so on board, we're going to need to initiate sleeps, shutdowns. Some of that is going to be driven by parameters that limit, very short sleeps or very short awake periods. Additionally, right, we want to try to run activities right, so we don't want to be sleeping all the time. So if a mandatory activity could be scheduled without violating any constraints, we're going to schedule that in favor instead of a sleep. Same thing, if we could get optional activities in there without violating its constraints, we're going to schedule that optional activity. And only in those other cases where we can't do anything else unless we could go to sleep, then we're going to do the sleep. There's also some constraints on sleeping too much. We don't want to remain at a very high state of charge all the time. Apparently that's bad for battery life, so we're even going to take that into account and try not to sleep too much. That's going to be parameterized. In fact, in the case of an activity failing, or getting aborted, we also have these special activities called cleanup activities that establish a known state, and they're just going to run a sequence, do the cleanup. This is an off-nominal thing, but it is taken into account as we establish our planner architecture. An abort, okay. So this is where the planner actively stops a running activity. So not only is it scheduling, but it actually has a monitoring function as well. And if activity is overrun its cutoff time, it's going to get aborted. If it's running and we hit that hard stated charge limit, it's going to get aborted. Optional activities, again, these were the nice to have ones, we're going to be particularly strict against them. So if they run over their duration, they get cut off. And typically the effect of an abort, we're changing the activity state, stopping it running, and then most likely the planner is going to run a cleanup activity after the abort. So conclusion here, I think I've showed you some of the features that we want to do. For the 2020 rover, we want to increase autonomy. We want to do the onboard scheduling that I've described. In particular, some new capabilities are the onboard power estimation, onboard sleeping, doing the preheating. We discussed constraints that the planner is going to have to manage as it's doing its schedule. We've showed an enabling set of knowledge, right? So a lot of this knowledge has to come from the ground. The ground has to tell the planner what does an activity consist of, what resources is it going to consume, what are the constraints. So there's a lot still of knowledge that has to be uplinked. Still, on the whole, we hope that this improves the mission, and we really want to enable more science, right? So more activities running on board, utilizing those extra onboard resources that we really couldn't do on MSL if there was extra time available, if there was extra energy available. Let's run some nice to have activities that the ground provided us. And let's try to reduce the workload of the ops team so they can actually get done in 5 hours. We're helping out with that with autonomous sleeps and preheats, reducing some of their workload. And as I say, this is all so far very early prototyping, so we're kind of just discussing the architecture. But future work, we're going to continue our prototyping and development, and one of the early things we want to find out is from our prototype, let's find out the RAM and the CPU usage, and that will help guide our further implementation and further design decisions. All right, that's what I have, and I'm happy to take questions.
Hold on, let me get a microphone so we
Or not.
Okay. What do you think? Give it a try.
Test.
Nope.
Okay. So what jumps out is that the planning of activities seems to become an optimization problem. So have you guys thought about, like, is there a specific solver or solution that you're going to implement, right? Because if you have multiple optional activities, for instance, well, maybe 2 of them cuts off the end state of charge, but maybe
Sure.
you could actually get 3 different ones in instead, right?
So the question is, have we chosen a solver, say, or are there lots of... And the answer is, well, first, we're early in prototyping. I will say, though, that this is real time. And so we're very much not trying to do something that is optimal. We are trying to do something that would fit in our available onboard resources, which is a very slow processor with very little RAM. And so to me, it's more important to be timely and correct. So I want to make sure that all plans and schedules we execute are safe. They may not be the best one, but they cannot violate the constraints, and I think that's the most important thing. And then everything after that is sort of, yes, maybe we can do some more in terms of, improving performance, but I would never use the term optimal for sure.
But if that being the case, then it seems to diminish the value of this, right? Because then it's just going to basically execute what you would have already told it to execute.
Well, I think the advantage is that what it does is it takes advantage of onboard knowledge that the ground couldn't possibly have, such as, I finished early, I have more energy. And so there's a chance that it can fit more in there. So it might fit in something, but and that might not fit in the best.
Okay, so it's more like a simple, like sequence logic.
Yeah.
Update.
Right. Right. It's definitely not a planner in the planner sense. Yeah. There's one in the.
So I have a question about the relationship between activities and sequences. So taking a picture is something you do all the time, but where you're pointed may be different. So is the sequence uploaded specifically for the activity, or is it a canned sequence
Right.
where the activity is passing parameters?
Right. So the question is, are the sequences sort of canned, or are they specific to that particular day's objective? So let me tell you what we do on the legacy system first. So typically on the legacy system, most sequences are customized and re-uploaded each time. There is certain ones that we can reuse, but for the specific day-to-day things, it's not just changing an argument here or there. It's actually a new sequence. So that was true even in the legacy system, and we anticipate that will continue. That there would be what we upload would be sort of fresh each day. Now, having said that, there's all sorts of ways you can use tools on the ground to help you out, so that it's not perhaps handwritten every single time, right? So we'd probably the more that you're talking sort of about it like a template. And that sort of thing, we would do some on the ground, some in flight, but typically sort of a new upload every day sort of thing.
What language are you using and why did you choose it?
So the Mars 2020 rover is highly inherited in terms of hardware and software from Curiosity. Curiosity is written in C. Most of our flight projects are written in C with a tiny bit of C++. And so we're continuing, because of largely the inheritance story, to go with C.
Okay, we got time for one more question. Hold on. Wait. This might work.
I was just wondering, are you leveraging Casper for like your planner logic, or where's your baseline coming from?
So not supposed to talk about implementation too much for ITAR reasons.
Don't worry about it.
But I will say we have Greg Rabideau on our team. He has a lot of experience with planners, and he's a great guy, so glad to have him aboard.
Okay. Very good. I think if there are more questions, capture Eddie in the hallway. It's 10 o'clock. Thank you, Eddie.
Sure.
Okay, let's take a. We're almost on schedule, and this doesn't. Why don't we take a break for 10 minutes? Come on back at 10 after 10, and Ryan Slaybaugh, are you here? Okay, you're next. 10 after 10.
Checking 1 2 1 2. Check check. Check 1 2 1 2. Check 1 2 1 2.
like this, people will pour in the doors. This is just excellent. Okay, does everybody remember what you have to do? There's a raffle. We're going to have information about dinner coming. I told you where to get lunch. You probably found the restrooms. Did everybody find where the coffee and the snacks are across the breezeway? Heads are sort of kind of going up and down. Okay, that sounds good. Our next speaker is Ryan Slabaugh from Lockheed Martin. And let's get you, is this it? No. So let's close that and get you, nope, nope. It was here a minute ago. Isn't that you?
Yeah, that's me.
Okay, here you go.
All right.
Thank you.
All right, so my name is Ryan Slabaugh from Lockheed Martin Space Systems Company. The work I do there, I'm a flight software developer for the small spacecraft and payload flight software product line. Today I'm going to talk to you about our past year of collaborating with the Center for High Performance Reconfigurable Computing, sponsored by the National Science Foundation, also known as SHREC. My counterpart that helped me put these slides together, Patrick Govin, he's unable to make it due to finals in school. However, I'll try to do his slides justice. And so the theme for this presentation is we stood up NASA's open source core flight system running on RTEMS real-time operating system on the SHREC space processor. All right, so the agenda, I'll talk a little bit about the motivation of why we went down this path of doing this work. Talk about a CUBE satellite called Skyfire and their flight software baseline. I'll then talk about the SHREC space processor for those of you who may not be familiar with it. Tie in what we had to do to stand up this software stack on top of the SHREC space processor, and then wrap it up with successes and future work. All right, so motivation. Lockheed Martin is building a CUBE satellite called Skyfire. It's a part of the NASA Next Step program. It's going to be 6U form factor. It's going to get a free ride on the Space Launch System in 2018 with the Orion Exploration Mission 1. So that mission, the SLS, is going to put us on a lunar trajectory. And really, Lockheed Martin is developing this CUBE satellite as a demonstration platform. And so one of the big things that we're trying to do with this satellite is demo new infrared technology. And so we'll be taking infrared pictures of the moon and sending those back to NASA. Additionally, us as the flight software product line, we're looking to demonstrate some new technologies at Lockheed Martin, which would be flying the core flight system, as well as flying the SHREC space processor, and then actually RTEMS as well. And so those are all kind of new things for Lockheed Martin. And so this right-hand graphic is the concept of operations for the Skyfire CUBE satellite. We're on the hook to deliver it in early 2018, and it's going to launch hopefully by end of year 2018, get that lunar trajectory. Mission duration's about 3 to 4 weeks. And really, we're trying to just get those images of the moon and downlink those to NASA. And then we have our own agenda with the flight software, obviously. All right, so here's a graphic flight software stack for Skyfire. You'll notice at the bottom we have the SHREC space processor, which is a multi-core processor, and I'll talk more about it on the next slide. Just above that, Skyfire did a trade down selected to RTEMS real-time operating system for the OS. I'll talk more about why one of the key drivers there. And then moving up from there, those of you familiar with the core flight system, you'll recognize the platform support package as well as the OS abstraction layer. We have names for the ones that we developed for this work. And then the Skyfire baseline is going to fly all 12 of those NASA open source applications, as well as a handful of mission applications developed by Lockheed Martin, and those all talk through the software bus that the core flight system provides. And so what you see in the purple dotted lines, This is a software product that Lockheed Martin calls the Flight Software Common Core, and that heavily leverages the core flight system in addition to Lockheed Martin proprietary software. So we have a timeline over here on the left. Just an editorial note that 2015 denotes the end of 2015, not the beginning. I didn't catch that before public release. It's a little confusing. So at the end of 2015, Skyfire announced that they were going to fly the Flight Software Common Core. And then early 2016, they down selected to RTEMS for their real-time operating system. About mid-year of us doing this development, we were able to accomplish the Flight Software Common Core running on RTEMS on the COTS development board that has the same Xilinx Zinc system on a chip as the Shrek space processor. It's called the Z board. Shortly after that, we upgraded to the Core Flight System 6.5 release, and that was extremely painless, which was fantastic. We were really excited about that, how easy it was. And then in July, we were actually able to demonstrate the Flight Software Common Core running on RTEMS on the actual EDU Shrek space processor. Okay, so the Shrek space processor, if you're unfamiliar with it, the Shrek group set out to develop this space processor that was high performance, however, low power consumption, as well as some other aspects such as reconfigurable and reliability. And so they achieved this by using both commercial off-the-shelf parts as well as some rad-hardened parts and rad-tolerant components on the space processor. Also, they had a goal to make this space processor much more affordable than the ones that we're familiar with, such as the RAD 750. And so these boards, the flight processor is roughly $30,000, and then the EDU is less than $10,000. And so that's essentially the onboard computer for the Skyfire vehicle. And so standing up RTEMS on this Shrek space processor with the Common Core, there were some hurdles that we had to overcome, but one of the drivers for picking RTEMS was that they already supported the Xilinx Zinc board support package for both the Z board, which was that development board I talked about, as well as the KeyEmu emulator target. And so from there, we were able to work with Shrek to develop the board support package for the actual Shrek space processor and not the Z board. One of the key differences is that the Z board uses NOR flash and the CSP uses NAND flash. And so with that, we had the students at the University of Florida develop a NAND controller driver, as well as we had an intern this summer who did a lot of the work for the SPY driver for RTEMS on the CSP. And so we're getting pretty close to having a pretty full functioning board support package for the Shrek space processor and RTEMS. Some future plans that Shrek still has on their agenda is to develop the Xilinx Zinc device configuration driver, and this is going to allow reconfiguring that FPGA during runtime via software, as well as some FPGA scrubbing. And then also, all the development that Shrek has been doing for this RTEMS board support package is currently only available to Shrek members, such as Lockheed Martin and all the other industry partners that they have. However, they do have plans to get a lot of this development pushed to the RTEMS GitHub for anyone to have. And so it would just be another BSP that RTEMS can advertise they support. All right, so like I said, our Flight Software Common Core heavily leverages the core flight system. And so one aspect that we had to work on was the operating system abstraction layer. And so what we did is we actually, so out of the box, core flight system provides a RTEMS operating system abstraction layer. However, it was for RTEMS 4.10, and it didn't have the runtime loader at that time. And so it was using additional piece of software for a runtime loader called CEXP. However, CEXP we found did not have ARM support, and so we didn't want to battle with making it support ARM. And so what we did instead is we started with the POSIX OS abstraction layer, and we just did the little bit of porting we needed to do to make that run in RTEMS, because RTEMS is a POSIX compliant operating system. And so anyone that stood up a new operating system on a new piece of hardware will definitely attest to there's a lot of challenges you have to work through. And so some of the challenges we had in getting this POSIX RTEMS OS abstraction layer stood up, initially we ran into a caching problem after the applications were loaded, where we had to do some flushing of the caches in order to load subsequent apps. Additionally, we ran into another cache-related problem, however, completely different, and that was in the runtime loader itself. And this was causing us, for our section headers of the applications, to get overflow buffers. And so we would even though our string table was in our L file, when we would load it in RTEMS, it would not show up. And so I'll talk to these bugs that have mostly, I think almost all of them have been fixed in RTEMS mainstream, which has been really good on the RTEMS developers to fix those. Also, we found that the runtime loader initially was unable to handle weak symbols, and so we had to do a patch where we were forcing all weak symbols to be force strong at the linker step. And like I said, it's a POSIX compliant OS. However, even when I do stuff with other real-time operating systems that advertise POSIX compliance, there's always a few gotchas, I guess you would call them. One of them, primarily, I've seen this in other OSs, is the SA restart flag for your timers is not supported. And so the POSIX OS abstraction layer uses this restart flag, and that's so other system calls get restarted when the timer triggers. So without that support, we had to figure out how to work around that. Another very minor bug was that the DL air was non-conforming to what it should be, essentially. But that was an easy workaround, and I'm pretty sure that's fixed already as well. And then one thing we noticed before we transitioned to CFE, or CFS 6.5, was that there was, it looked like the initialization thread priority was hard-coded. And it was a lower priority such that in the real-time environment, when we load our application, some of them were preempting the OS init, and so that was causing issues. However, in 6.5, that's been corrected, and so it's really a non-issue now if you're using the latest release of Core Flight System. So the platform support package, that's the one that's kind of right there tangential with the operating system. And so this is where you implement the hardware-specific details and the kind of the bootstrap code that calls the OS at init. And so we had to do a little bit of porting. Again, we started with the PC Linux that was delivered with Core Flight System, and we just did some minor tweaking again to that POSIX implementation to make it work with RTEMS. And so that was really helpful for us because we didn't have to modify it much. We did do some proprietary things in there, specifically for our Skyfire mission. And then we switched the 1 Hertz wake up that the OS requires in Core Flight System. I think that was using signals originally in the PC Linux implementation, and we switched that to a timer server in RTEMS. Again, challenges associated with doing this porting for the platform support package is we had to resolve our undefined symbols, which was a little bit of a bear. I guess the way we can do it is use NM to find all the undefined symbols and just force them in with a linker argument. However, we typically just load the applications and it'll tell us which ones are undefined, and then we go and force them in. So kind of brute force. And so our successes and challenges in standing up the Flight Software Common Core on RTEMS on the Shrek Space Processor. So big success is that we do have the Skyfire software baseline running on the Shrek Space Processor, and we're doing functional verification testing with our ground system in the loop. Huge thank you to NASA for making the 6.5 transition so easy. Literally, it was very simple to upgrade, and so if you haven't upgraded to 6.5 by now. Don't be scared to, it's very simple. And then huge thank you to OAR and RTEMS. They've been super supportive of us, and we use our Shrek community to submit the tickets for the bugs or issues we found with the runtime loader primarily. And we've gotten great support from RTEMS to fix those patches and update the mainline. Also, starting with the POSIX, OSAL, and platform support package, that was a huge help for us to get it ported over to what we're calling ARM RTEMS. And then we also call it RTEMS POSIX for the OSAL. And then some challenges is, I think we were the pathfinders for the RTEMS ARM runtime loader because it seems like a lot of issues we ran into was kind of just like the first people really beating on it. But luckily, we've done that legwork now, and so like I said, a lot of those have been fixed on the main line, and so if you go and try to do this yourself, there's probably a lot of hurdles that we had to jump over that you wouldn't have to yourself. And then porting PC, Linux, OSAL to ARM RTEMS, we had those few challenges with like the SA restart flag. We had another issue with signal masks that was causing our scheduler to not operate as we desired when running on the embedded target. So future work, Skyfire, like I said, they're going to have to deliver this early 2018, so they're going to begin their software, hardware integration testing, continue doing that functional verification testing, as well as the University of Florida, or I should call them Shrek because they're transitioning to the University of Pittsburgh. But they're going to continue to solidify their NAND controller driver that they've developed in RTEMS and deliver that to us. And then Shrek, like I said, they're moving to the University of Pittsburgh, I think this coming semester in a few weeks. But they're going to continue increasing their RTEMS support for the Shrek Space processor and try to get all of those, all the development they've done pushed to the GitHub. And so that way everyone has access to it and we can continue to build up the support for the Shrek Space processor. And so I think with that, I've probably caught us up on time, and I'll open it to any questions.
Are there questions? Here.
Wait, Joe.
Did you have a hand?
So actually, I'm the one who took your name tag accidentally this morning, so I'm sorry.
Oh, I have mine from yesterday, I guess.
Mine was right by yours. So thanks to you guys for blazing through the ARM, and y'all had some of the C++. I think all of those are now fixed. I agree with you. I don't remember the SA restart and the DL error, so we need to fix it. But in case anybody's not here all week, we think we're technically complete for 4.12. There's some documentation and some new hosting issues on pointers to the new documentation. But so if there's Shrek stuff that needs to get merged, we need to push on all of y'all's tickets to make sure that they're dead before, because we're probably, we were hoping before Christmas, but nobody works really well before Christmas, so it just didn't happen. So it'll probably be 1st of February, I'm guessing, but for 4.12 branches.
Okay.
But thank you guys. It was nice.
Yeah,
well, let's close your tickets and make sure y'all are all happy.
Okay.
Very good. Any other questions? Here, catch.
Just trying to establish scope for the OSAL, BSP, PSP development effort. About how long did it take and what was the team size?
So we've been working on that effort really since the beginning of the year. I would say it's a 6-month effort probably before we had things running on the Z board. And it was pretty seamless to transition to the Shrek Space processor after that. And our team, pretty small team, less than 10.
Cool, thank you.
Mm-hmm.
Other questions?
Early in the presentation, you had notes about using QEMU.
Mm-hmm.
So how much success have you had with that? And would you say there's a lot of value in using it, or was it just too dissimilar from the hardware?
No, I think it was, the biggest value we gained from it was one of those problems we had with the runtime loader where our string table was overrunning the buffers at load time. And so we could actually use KeyEMU or QEMU to debug, because when we would run it on the emulator, it wouldn't cause a reset. And so on the hardware, the board would just reset it when you hit something like that. But on the emulator, it would actually print out what the error was. And so I would say the most success we've had is debugging problems. We don't use it much as an emulator, just because we're not that familiar with it, and it's not that simple to get like commands in and out of QEMU.
Any other questions? No? Very good. Thank you, Ryan.
Thanks.
Is Scott Tashakor? I've said that. Did I say it wrong? How do you really say it? Tashakor. Thank you. Okay, so let's put this down. Get you set up. Somewhere in the pocket region on the collar. And let me get your presentation. Yes. So forward and back and laser point. Okay. Wherever you like.
All right, I'm Scott Tashakor, and I'm from the Marshall Space Flight Center, and I work in the flight software division out there, so we do all sorts of stuff. I'm going to be talking about the automation of our software regression testing today. And for those of you that use UT Assert on CFS, you'll notice a lot of similarities. I was noticing that yesterday. So just to give you an overview of what I'm going to talk about, I'm going to kind of introduce you to everything and kind of the situation, tell you what the requirements were that we ended up having to fulfill, give you kind of how the test harness set up using its modularity, how we put in inputs, how we compare our outputs, and then when we run the test cases, and in the end kind of give you some conclusions and how well it's worked. All right, to introduce it, this has been developed during the Space Launch Systems flight software development. SLS, for those of you that don't know, is a man-rated heavy launch vehicle. It is being developed at NASA with a lot of outside contractors helping to provide hardware and other resources. The flight software for the vehicle is being developed in-house at Marshall, and so we have Boeing flight computers that we are actually writing the software for. Boeing gives us the drivers and everything, so we're not at that layer. Flight software, we provide all the computer functions, so we're doing all the communications, telemetry, control of the vehicle, and everything to that. And at Marshall, we're using an incremental agile software development. Agile is in quotation marks here because we've deviated from the I guess the standard is what you want to say, but I'm not going to talk about that. There's actually another person here from Marshall that is going to address a little bit more of that tomorrow. I don't remember what time. So, but it was to try and it was to keep working through everything is how we did it. So for the requirements for the test harness, we needed to be able to continuously test. And this came into fact based on our agile development of where as we would put in new functionality or either the requirements were originally made, we had to make sure that we continually tested them to make sure they were still being met and was not getting messed up with any new functionality added. Originally, this was supposed to be informal for testing of the requirements, but the independent test teams ended up liking it, and so we went through the formal qualification or the formal testing to checkbox the harness itself. And so now our formal independent people are using this to test some of the design level requirements as well. So it's already gotten recognition. It was for independence testing, so we would end up doing standalone software of where each person, when you're doing like the main propulsion system or the control algorithm or whatever, everyone is written in a little class, basically in C++, and so everything is modular. So everyone is standalone. You just have your publications and your subscriptions that you end up doing. You can also use this to test the functionality of certain routines inside. If you're trying to work on something specifically, let's say a functionality of a fault management or whatever. So we had to be able to provide that. It had to be configurable to many different many different uses, such as control algorithms or valves and all sorts of other different things. But we didn't want people to have to go in and recompile from scratch every single time. The inputs themselves, we had to make sure that they were maintainable. And so we ended up making sure that that it was not a singular, like one person had to do it. It needed to be maintainable among different people, so we kind of abstracted that away. I'll get into that later. We wanted to make sure we could vary the scenarios through parameters of like configuration of the software itself, the phases during flight, and if we wanted to do any off-nominal testing for any just random stuff that you want to put in. And then ultimately, we needed to make it automated to continually test it as we were doing it earlier. Because if it's done manually, people are going to forget or they're not going to want to do it. So to kind of go over the initial setup, we have a base class, which I consider kind of the harness infrastructure class. This is kind of the abstraction layer for the operating system. It provides a lot of our file input and output. It sets up the harness, such as just registering all the different tests among each other. This level, we will make the operating system calls and configurations. We provide some generic comparison utilities so that people can specify what they want to compare and how much tolerance and everything for floating point values versus integers and different things about that. It also provides general system emulation, so it kind of gives the overall, if you're trying to go through like a military 1553 bus, we have some generic libraries to kind of emulate that and put in through, but it's not the specific implementation because you did not want to be dependent on the actual one. The test harness setup. So then what we end up doing is we derive from the harness infrastructure. So every module that you're trying to create, you basically derive a class from that harness infrastructure class. This class is where the initialization of the software occurs. So you would set up your any configuration things, such as your parametric values or like persistence counts, times that you wanted, anything that's supposed to be kind of low level. You can set up a lot of the module specific support if you needed to set up structures or publications and everything, kind of global flags like that. The thing to note about this is that we wanted to keep it independent among each module. So each module class is independent and it's just getting called by a known base class or by the function in the known base class. It also provides the fault interpretation. So at this layer, we end up putting in like enumerations for if there are flags that we wanted, or when you have it from your configuration, so you can make a nice little enumeration that gets interpreted into a specific Boolean or a specific fault. You can set values of different things. You can set the length of time that the system needs to run or your tests need to run, but it continues on. So after that, each Each module then has another derived class, which is kind of its specific set of cases. And this has ended up getting, it starts to get a little bit more complicated here, but this is where you set up your specific support for a group of tests. So as we're going through, for instance, with the Guidance, Navigation, and Control, or GNC, they have a lot of history because they have a lot of filters and everything in their code. And so here would be where you could set up in their history values, since we did not want to have a lot of file I/O going through because the systems were never set up for that, running on the actual hardware. So this is where we put that in. We could subscribe to that, kind of the pre-calculate what it should see or what the inputs are going into, and then build up anything. It also provides it provides the specifications of your comparison, so you can specify what variables you're going to look at and what's the tolerance and expected value range you're supposed to be into. So you have that. You can also specify any like output flags or any printouts. So if something fails, you can print out and say, here's printing out what has failed and how it's gone wrong. Then off of that, now we get to the specific test setup. So each one now has a specific test that gets called from the individual case class. So we have set it up so it's a comma separated value set of inputs, and so that way you don't have to recompile it. You can continually just update the CSV file that is loaded from the initial harness infrastructure and kind of go on with that. We also have, so the inputs, and since these are kind of all customizable based on the user, everyone can set up their own little things, but normally what ends up happening is you set up your specific inputs that you want, and then at the end of it, you have, here are all the outputs. This is kind of my expected output. So if you're looking for, is a flag set? Did we correctly detect that fault? Have we done anything with a specific flag? Are some of the intermediary values what I expected them to be? So you can set that up afterwards, and in the CSV, this is where it's read in and used for comparison. At this level also, you can specify what fault by just multiple ways. You can set up one way I did it was to set up a counter to say I have a number of faults on this case, and at this time I would change it to, let's say, 1, and then set the faults to whatever variable that I want through a specification layer. So you have all sorts of differences that way. So running the test cases. During compilation, we actually compile the full set of flight software. The reason being is that we wanted to make sure that it's always fully getting compiled and that the unit tests are staying in sync with the actual flight software itself. Because if not, you would have some of the unit tests that would just be old and they would say everything passes even though the actual flight software itself is not working. We have conditional compilation of the test modules based on a bunch of macros and pound defines to kind of determine what level you're trying to compile in. So if you're not looking at the main propulsion system, there's no point in compiling in those tests. So it helps for a smaller set, or if you know that there was a new release of some M&FM algorithm or anything that way, and you know they're all going to fail, there's no point in running it until those have been updated. We compile the software for the development unit, so we're actually running on what is supposed to be a complete representation of the hardware. It's not the actual flight computers, but this is what we had, so we were trying to make sure that we had as close to the actual architecture as possible, just in case for that there were different calculations based on floating point units and everything. The inputs are, as I said, are loaded via a CSV file, and all the comparisons are done that way as well. We ended up making it so that the outputs are simple pass-fail. Are you within the tolerance that you specified, or did you get your expected value? And what ends up happening is we go through and count up the number of passes and fails, so you can count out how many tests pass, how many fail, put up little warning printouts or whatever you want. But it also gives us a nice little summary report that we can then look back later at and say, hey, we've failed this many tests, where are they? The tests are run through a file specification as well, so what ends up happening is you have a list of what tests individual tests you're going to run. The reason for this is that if we have it compiled in for the module, the test module compiled in, but the test is not run, you get a notification saying that these tests were not run, so not to expect it to be working. So even if you've compiled everything in, but you only want to run through a specific set of tests, you can still do that. A lot of the automation of this has gotten built up because we were trying to look at a way to do this. And so the automation, we've ended up automating it through Perl and Python scripts, or I've done it through some Bash shell scripts. People have also used Jenkins for complete build things, and so we get nice little reports, and then some unfortunate person has to email those out and try and make sure that people fix those. But so the advantages slash conclusions, the execution support was, it was for multiple independent cases. That's what we were trying to keep up, so that you could specify whatever module or whatever set of cases you wanted. The developers have the ability to specifically and precisely specify what they're testing, so we have no requirements on, or no restrictions, I should say, on what they're specifically testing. So as you make your module, as you make your class, as you make your test, you can specify how in-depth you want to look at, as long as it's accessible to the harness. There's the ability to add automation multiple ways, because everyone has a different way that they want to look at it. So hopefully it can get expanded to other people or other tests. The harness itself can be executed continually, so we can put it through the build scripts if we wanted. We can run it weekly or daily is what we were down to. And if I remember correctly, we're up to about like 20,000 some odd tests, but that's continually changing. Granted, the majority of those are GNC because they end up doing a lot of filtered histories, and so we have to build it up. The approach can be adapted to support other projects. As I noted earlier, the CFS people seem to have a very similar approach to their UT assert. But that's really all I had. So should just be questions left.
Are there questions? Hold on, let me throw you a microphone. I'm going to go up.
So do you consider these unit tests, or are they, do they test the integrated software? It sounds like you're compiling in your test, right, right into the software?
Yes.
And so they're testing one module at a time. Do you also have additional unit tests that you run prior, or is this it?
This is it. These are our unit tests. We don't do the integrated tests. We do that with a different system because it needs full feedback and everything. But yeah, these are just the unit tests.
And are your developers who write the code actually develop these tests as well at the same
Yes.
time or after?
Yes.
Yeah. Okay. Thanks. I'm Dan Rom I work at the Space and Missile Center here, and so in our program office, like for our future programs, we're looking for ways of having the contractors automate their software tests. I guess not more like integrated testing of a full system. So I know you mentioned Jenkins, but is there any like commercial or open software package that could be done? Have you considered anything like that? It looks like you've really, this is more of a homegrown system, but that's what I'm looking for.
I can't really speak to that because I don't know. I had joined the project afterwards, and they didn't have enough money to support anything else outside, and so this is what I ended up coming up with.
Okay, thank you.
What language are you using for the flight software, and why did you choose it?
The flight software itself is C++. Why it was chosen, it was before my time. So, not because I'm young, but because I joined a little bit later, just to clarify.
So do you write test classes for testing base classes, or just like test module classes? Like if you run your test on a base class, it is supposed to pass the same test on a module class?
Yes, you could. I mean, there's no reason not to. I mean, most of it is straightforward. You can specify whatever you want to test it on. If you wanted to, and that was what I was trying to make sure, that we could test it on the base class itself all the way up to, well, you have one little function inside that you're trying to just mess with.
Just wondering if you considered having, in addition to this, maybe a Linux port, and maybe in addition that might help, doing faster development of, quick turnaround versus running on actual hardware all the time.
So the reason, okay, that's going to bring up a little bit longer of a discussion, but basically what it came down to was that since we're running on an ARM Power PC, the endianness is different and the floating point units are different. So you get different representations as well. And so what we're trying to do is make sure that everything would work as it is, as close to the hardware as possible. Because as I have found out, our GNC people, they write all of their stuff on Linux implementation on an x86 64-bit machine. And what is ending up happening is we've branched a couple different ways, because the Intel architecture actually has a 80-bit floating point register, so it's actually storing extra information, and that little difference can end up accumulating in a calculation, and all of a sudden you branch it a different way and say control an actuator to do something slightly different.
Okay. Any other question? Okay.
You mentioned for your test cases, your individual implementation of test cases, that there were CSV inputs and comparisons for how you specify the test. Where are those schemas kept, or how did you organize how the schemas were, implemented?
Basically, I mean, that is again based on, let me go back. It's at this level here, the test case class, the green. The users themselves can specify what order and what things represent. So at this level, for instance, instead of writing out true all the time, I made a enumeration that was just like T. And so you can put it in whatever order. A couple people have done it, so you specify like the time that this event occurs at, and then some of the different inputs, and then you get your comparison outputs. But it's really left up to the user.
Okay. Thank you very much. Well done. Well done. Did anybody have a recommendation on test tool? Favorite free open source test tool? Say it real loud.
So there is a continuous integration server which is called Hudson. It is pretty good. I have used for flight software program that works very well.
So Alan?
Yes.
Depending on the language, there are different available for free unit test harnesses available, such as C-Unit, and there are several others.
No.
You just hook them up to Hudson or Jenkins or TeamCity or whatever you're using. You can build.
We're done then, huh? I can't believe this. This will take but a moment.
It never takes a long time to log into Windows.
It's going to install an update. You know what? I have a faster way.
turns it on, do you think it'll be installing an update?
That's right. This is, those of you that don't understand fault management,
Got redundancy.
That's okay. No, hold your applause.
Okay.
Amazing. Okay. And now. But I have to show it
Yeah.
there.
Yep.
Yes, so if you could clip that on, that would be just excellent. Open this thing up. Properties. Nope, wrong one. Here, properties. Screen resolution. Find me another place. Okay.
There you go. It's up there.
Okay, look at this. In and out of safe mode in no time. Oh, I didn't even say who you were.
It's okay.
Okay, Brian Engelmeyer.
Engelmeyer, yes. Yeah, I'm Brian Engelmeyer. I am a flight software architect at Northrop Grumman in Baltimore. My co-author is Chris Mason, was a software engineer on the team of the program I'm going to be talking about. He could not be here today for this. We're going to talk about the benefits of a virtual systems integration lab, or VSIL. In order to tell you about this, I'm going to walk you through the chronology of how we built it up, what we discovered along the way, and how it worked out for us. Okay. So, why would you want to invest in a VSIL? As I'm sure most of us know, the EDU test benches that you get for building systems, they're expensive, they're limited, so you get one or two. There's a lot of demand for it with people from different groups that need it, from the integration and test teams, the flight software teams. Lots of people need access for that. Because of that, our program was seeing our schedule continually pushed to the right. And we reached a point where software was on the critical path, and we wanted to fix that. We didn't want us to be the problem. So we started investigating how to fix this, and we discovered within Northrop there was another team that was doing some virtualization work, and we looked at what they were doing and convinced our management to help to invest in building this virtual system integration lab for us. So we then started working on it. So what is it? It's our implementation is a hardware simulation using Wind River Symix that runs unmodified flight software binaries. It simulates the hardware from the software viewpoint. Yeah, I know some people here know Symix. We were going to call some of them in if we couldn't convince our management that this was worthwhile doing. Each user gets their own platform on their own desktop PC, so suddenly instead of 2 benches, every developer has one. You can run, as we'll show later, you can run flight software, test software, INT can use it, hardware verification teams can use it. So when we decided to invest it, we took 4 people and got our virtual payload up and running. It took about 6 months to get it running fully for flight software. It only took about 2.5 months for flight software to just start using it and start poking at it and seeing what was good, what wasn't good, what did we need to fix. And to give you an example, this isn't really our payload. Our payload has multiple single board computers, has 8 custom boards, and the total board count for mission requirements, to meet mission requirements and reliability and redundancy, is more than 25. So that's why it took so many people that long. So Symix is the technology that enables the VSIL. Symix gives you models of all the pieces of the boards. It models the memory, it models the flash drives that we use. It models the devices. There's chip level models. One of our boards has a 1553 interface. We could use the existing on a chip, on a 1553 on a chip, we could use the existing model for that, excuse me, and just drop that one in there. It runs everything from the kernel through the board support package, the flight software, all of it runs unmodified, so you can use it for all of those kind of things. There's no custom compile switches. The binary takes from there and goes and runs over on it. So it provides, one of the first things after that initial 2.5 month period when we started getting flight software on it, we started seeing some of the benefits right away. You could do kernel work, BSP work, and flight software development, all of it on there. It's an accurate hardware environment, so you can do all of that. You don't have to, well, let's wait until we can run our kernel on the right one, on the real system, and see what's going on. The model runs all, like we said, all of it without modification. Another big benefit we saw right away is that you debug by stopping the entire system. The models all stop. No more interrupts coming in while you're looking and trying to poke around. You can examine the state of the boards, where they are when you stop it. You can reverse the execution of the system. Our system is not really a hard real time, it's more just in time. So sometimes you end up with things running in different sequences. And how did I get there? How did I get there? You can stop it and back up and see what happened. How did you get there? So within 2 hours, we had a problem that was plaguing the team for 6 months. We had this random crash. It would happen like 3 times during a day, then we wouldn't see it for a month. Then it would happen again. We saw it. Fortunately, we saw it in the first few weeks of running the flight software on the VSIL. Once we saw it, now the board was not hung. We could look at it and see what was going on, figure out where we were. 2 hours later, we had the root cause nailed, and we could fix it. That right there made it worth it, just for that. It's also great for fault detection and insertion. We could add in our boards, the boards model the connections between them, so you can have checking in between there. You can have checking on the board to say, when you write to this register, 1 second later, you have to write to this one. If you're writing too slow, too fast, you can do that. You can test that in the model. The model can alert you when those kind of things happen. So you can get timeline verification. You can insert faults from the hardware boards through the VSIL, because you can build an interface from the models themselves into the board. One of the biggest uses we've had for doing that is we can insert flash memory faults. Our boards have a flash drive that at boot up we load the flight software from. So we're able to insert block level recoverable and non-recoverable errors and make sure that flight software detects it, that the kernel detects it, that flight software detects it, that our recovery operations work. We can do all that without damaging any piece of hardware. Let's see what that. So our big selling point was to tell management, we're going to pull the schedule back. But that's kind of a wishy-washy thing. So the way we tried to tell it was by tracking cost avoidance. So basically we said, we put in a timer so that we knew when developers were using the VSIL and we knew how long they were using. And we were trading that for hours towards the end of the schedule to try to pull that back in. And we were also tracking at the same time real hardware availability to say, one of the hardware guys took the bench and took it apart, so we couldn't use it for 3 hours that day. So those are 3 hours we didn't have it, that we did get more, that we got more benefit from having the virtual SIL there. So we used that to track it. And then that's also tracked against the cost of the standing army at the end of the program when, sorry, you only have 6 hours of time on the bench, but you've got the entire flight software team there for 8. So that's a standing army that you have to absorb those kind of costs. So as you can see on this chart, maybe not. So we broke even about 4 months into it, and at 6 months we doubled our return on our investment, and it's been continuing to grow since then. I think a better marker of pulling the schedule to the right is that, so we started this in 2014. We have had the VSIL running all of 2015. Earlier this year, we had board flight software engineers because we were meeting all of our requirements, and we haven't gotten to payload INT yet. So we're now using them to work on the VSIL to work for building new capabilities that we were going to be delivering after delivery. So I think that gives a better answer than this, but management likes to see this kind of thing. So before I can go into some of the other benefits, I'm going to talk about our testing framework that we have. It's Atlas, which is ATO, which is the building we're in, an acquisition and analysis system. It's a reusable framework for testing, performance testing, functional testing, calibration testing. It works everything up from board level INT all the way up. We track all of the information. It provides control of the STI that you need, control of the payload or the unit under test. Gives one-touch control from the operator's console for running all of these things, and it provides automated pass-fail. When you do an analysis after the acquisition, you get it, and it's all stored. All of this is stored in the database. It also stores all the telemetry from the STI, all the telemetry from the payload, as well as the payload output files. And the results of all of these activities are stored, so you can do a lot of data mining to go find out what you've got. So why would we want to use Atlas with the VSIL? When you look at the VSIL, it's not just a flight software tool. It runs flight software. But now that it's running flight software, it can be used by people that need to use flight software to do their tasks. So you could do system and flight software test development. Atlas runs tests that are go run this scenario. So you feed these files into the payload. This is the expected output. All that development has to happen. And previously, that was one of the things that was tying up the bench. So again, the test software team now can use this. They now have a fully functioning payload on their desktop. So they were using it. So that's for both flight software and system test and development. We wanted to capture all of those to track the problems. Where did we start seeing this problem? Somebody thought they saw it 3 weeks ago, but we weren't sure, so we wanted to track all those, and that's what's always captured in the database. We also have hundreds of existing testing scenarios right now, and we want those to be able to be run by anybody. The flight software team should be able to run performance tests and make sure that we're still doing that. So instead of writing their own version of that to feed in with a different tool, we want to be able to use Atlas. So to integrate Atlas with the VSIL, we first had to take out the STI, but that's not a problem. Atlas is built to be configurable from the ground up, from when you first start getting pieces showing up all the way up to the full payload. So that was not a big problem. Then we have to replace the unit under test with the VSIL. So we pulled it out and put it in. That was a little bit more. We had to teach Atlas how to run the VSIL, how to spawn it, how to talk to it. The bigger problem was there's a bus emulator that's part of Atlas which feeds the 1553 into the payload. The 1553 is no longer there. It's a virtual 1553. So we had to have the bus emulator understand how to send messages into the VSIL model, and the model then places them into the 1553 chip at the right time. And the right time being the VSIL time, not wall clock time. When you're running in the simulator, there's at least two different time bases you have to keep track of. One is what's the payload time, and one is what's outside time. So that was a little tricky to get it going, but once we got it going, it's been rock solid since then. So I'm going to go back and look at why really run with it. The real reason is our release rhythm. For flight software and test software, we were doing weekly or fortnightly builds, and we were doing full regression tests, or partial regression tests on those. We had an engineer coming in at 2 in the morning to run those. That's just not right to do to somebody. But that's the only time we can get the bench dedicated for 8 hours to run all these tests. And then monthly, we're doing the same kind of thing, except we're doing full up regression tests, not targeted ones based on what changes were made that week. So we wanted to replace this with nightly automated testing, which is really nice because now nobody's worried about the hardware. It's not expensive. It's not going to go over temp. You're not going to have to worry about a power supply going wrong. So the first thing to do is we got to take away the operator console from Atlas. It's the easy command line parameters. And the next one is we replace the operator with Jenkins. Jenkins, if you don't know, is an automated server to take out the non-human parts of software development. So it's perfect for this kind of thing to run that for us.
What is the operator doing?
Start up the unit, monitoring. So the test software, the flight software, monitor the payload and make sure everything's going okay. The operator's there looking at the displays going, yeah, the temps still look okay. Both of the software systems are supposed to shut it down if you're having problems, depending on the severity of the problems. But we don't want to trust that while it's in our hands and while we're developing all of this. So the operator's saying, go run this test. The results come back, go run this test. The operator is also the flight software engineer, the test software engineer. So they're going, run that test. Oh, no, recompile, reload, redeploy, run it. So that's what it is. It depends really on where you are in the system. So we replaced Jenkins. So implementing the automated testing was not that big of a deal. Jenkins is really nice to use. We previously had nightly builds going on with the results being emailed out just to see who broke the build on the latest check-ins. That was done as a cron job, so first we had to make Jenkins take over that. Once he did that, then we've got the full cycle, and in fact there's one more step in there that we've got, which is we do static code analysis as part of the nightly runs too. So that's also what Jenkins does. We run it on multiple baselines. I said we split the flight software into 2 baselines so we could work for future capabilities as well as the ones that are needed at delivery. He's also running testing flight software and testing test software at night. The results, we have a subset of the full tests that run nightly. On the weekends, we run a full set of tests because it takes longer than just an overnight run. It starts around midnight. Developers get the email results from Jenkins every morning. 7 o'clock, it shows up in your inbox telling you what's broken. There was one other thing on this, don't remember what it was. So other benefits. So because of our success on our program, other programs are starting to look at this. One program I'm supporting, we have the FPGA designers, the model developers and flight software defining the model behavior, get to define what the FPGA is. Like traditional development at Northrop is the hardware and the FPGA get done really early and the FPGA guys are gone by the time flight software gets there, and now we've got to live with what they thought we would want. Now we're working that at the same time, so we're shortening our development cycles, we're shortening our programs. That's working out really well. Even the FPGA designers like it because they now know what we do with it. They understand it and they can start suggesting things. The hardware engineers that are doing the hardware INT, they're developing their acceptance tests. The VSIL doesn't really have to run flight software. It can run anything. We run unit tests on it. It runs any piece of software you want to put at it. So the hardware engineers are writing their acceptance tests to test that FPGA interface. Using the VSIL, they can do it without the boards being there, and then when the boards are there, they've got a better shot at finding the bugs. It helps cut down their times as well. And we're getting to the point that we're going to have flight software running on the hardware before the hardware is available because of the VSIL. And that's our goal. So in summary, the benefits are it's a better development environment. It's accurate hardware. It works everything from kernel all the way up through flight software as well as other types of software. We can do fault insertion that we couldn't do before without going in and tweaking code or something like that. We can stop the entire system for debugging. We can do the reverse executions to find out where we got to. We're cutting down on cost and schedule because a lot of it is because of the ability for all these other software teams, even the ones that didn't think they were software, like the hardware INT guys, they're able to use it, and we can start flight software development before the hardware is available. And we're seeing an increase in reliability with the automated unit regression and functional tests. We get much more test like you fly capability now because we can just increase the number of tests. Fault insertion, and full payload is always available. With all the boards, you can imagine our EDU units are never fully populated. Now we have a fully populated system that we're able to run on. And I remembered what it was about the Jenkins. Chris Mason, who was the one that worked on that, added in, we run it off of a spreadsheet. It's driven off a spreadsheet. So anybody can add a test to run. They just put the name of it in there and then go say what days they want it to run. Nobody has to worry about knowing how Jenkins scripting. Less programming language to learn. We don't have to worry about teaching people that. It just works then. So what are our lessons learned? As with every simulation, you want to start small in your model first. We started with just flight software required. We grew from there, and it still gave us a lot of benefit at the very beginning. It still doesn't replace the full payload. Once we got onto the full payload, we had 4 minor bugs that didn't take us much time to figure out, and they were all timeline related, which then is another lesson learned is VSIL is another source of bugs. It's another piece of software, so you've got to monitor. If you see a problem on the real payload, but you don't see it in VSIL, you have to figure out why, and then feed that information back into the VSIL and get new revs on it. And iterate on the timing of the model. The board models need to provide the same timing as the hardware, but you don't have to do that right away. It doesn't have to happen right away, especially if you start really early. Just get close enough so that everybody gets a feeling for how things are going to work. And that's it. Have any questions?
There are actually a lot of people listening online, otherwise I wouldn't.
Yeah.
So one question, 2 observations.
Mm-hmm.
Did you guys do your own models? Because I know how hard.
Yes, we did our own models. So the SBCs, most of the pieces were there, but we had from various other places. But the rest of them, we had to do our own models, modeling all the connections between them. Some of the FPGAs have some really complex information that they have to fan out to other boards or feedback to flight software, and we're modeling that.
And then without, hate plugging Wind River, charging up, the thing that was critical for us when we did that the first time we got Symix is the Indian issues, which I don't think a lot of people are aware of. So if you're trying to simulate on a big Indian and running on a little Indian or vice versa, the old VX Sim just doesn't work. It'll kill you.
Yeah.
And Symix is awesome. And then another thing is wild memory rights.
Mm-hmm.
So you don't have to have an ICE unit. You know, you don't have to spend $30,000 for an ICE. You can just literally put a breakpoint on write.
Yep.
So
Yep. Yep.
Sounds good. More questions? Here, we'll go with this one.
So are your tests portable to any versions of hardware in the loop testing? So can you take the same test script controls and run the same models, but with whatever your versions of hardware in the loop platforms you have?
Yes, the tests are, yes. Between programs, they may or may not be. But so we can run the same script on the VSIL as well as on the real hardware, if that's your question, yes.
Yeah.
Yep, that's been our goal. The part that really cares about that is generally Atlas, part of Atlas, which is not the scripting part. The scripts are separate,
So on the model development,
Mm-hmm.
looking for a little insight into the scope of that work, relative to either the FPGA design effort versus the model design effort, and how you staffed it. Did you staff it with more software folks or hardware folks? What worked? and what
So
didn't
we've
work
staffed
there?
the model development with their software folks. And most of them are interns. We had a couple interns doing it. We had some right out of school doing it. Level of effort is certainly less, for a model, is certainly less than the FPGA, because you don't have to model all that the FPGA is doing. You just have to model the part that the software cares about.
What about
It's probably more complex than that, but our device drivers are pretty simple for our architecture.
Other questions? Yep.
Could you give us a better idea of the level of effort that it took to develop the VSIL? How many people, how long, and how much effort did you spend debugging the VSIL as opposed to debugging the flight software?
So, like I said, the VSIL was the 4 people full-time for 6 months. What we were modeling were existing boards, so we already had the acceptance tests that the hardware INT guys run. So we ported those into the VSIL and ran those as a test of, is that interface what we need it to be? Then after that, I couldn't really tell you about debugging one side or the other because we were spinning so much on, oh, this is great, I need it to be able to tell me this. And that just gets lumped in with, fixing a bug or, determining where the bug is, so, sorry.
Other questions? No? Yes? No? Okay. Thank you.
Thank you.
Okay, our next speaker is Joel Sherrill.
Stay.
Don't go.
There, now you're there.
Okay.
How they interfere.
Okay.
It would be RTEMS, wouldn't it?
Yeah, that's it.
Let's open it up.
Or F5. Oh, I'm not that good. So they better only go forward because if we have to go back, I'm in real trouble because that's too complicated. So for those who don't know, and I know you know, I've been involved in FACE for representing the Army for Army aviation for a number of years. FACE is an open standard trying to define both a technical architecture and a foundation for common operating system environments. And mostly the operating environment for the operating system is going to look very familiar. And RTEMS, well, there's forward already. So there's a space bar that works too, right? The first thing to know about is that FACE came about as an open standard consortium operated under the Open Group. It was started by Navy, NavAir, and Army Aviation about 6 years ago. And it operates, I guess you guys should know about, the NASA guys should know about OMB Circular A119. There are rules for how government organizations can participate in open standards. And this organization was developed specifically to allow government participation with industry. There's about 90 members depending on which month it is. So this is a very open market, competitive. It's supposed to be I can't say it. You can say that word? That's it. That's the word I can't get out. So there's supposed to be reusable software components that have defined interoperability boundaries, and there's the link. The key to the architecture is, if you looked at it from your standpoint and just threw CFS at this, the focus is on the CFS apps, which are the portable apps. They don't depend on hardware or anything. The transport service segment is comparable to the data bus in CFS, and you can correct me if I use any wrong CFS terms. The platform-specific segment is generally devices that change, but you always get the same device, like, say, a GPS. But the GPS may not hook up the same way, so you hook it up through an I/O service. And basically, the portable things you should be able to move from mission to mission. The other things, if you use the hardware, they come along, and then you reuse the data bus, right? The part I'm focused on is the part wrapped around the edge, which is the operating system segment. The operating system segment, when you get down to it, looks extremely familiar. It is there are 4 profiles, and the key is, if you notice that the fourth column is ARINC 653. So 3 of the profiles actually require ARINC 653. All 4 have different size POSIX profiles. So the security is very small. Security and safety base are small POSIX subsets. The first day I started on FACE, RTEMS naturally came within like 6 methods of having everything that was in the FACE profile. We actually have almost everything that's in safety extended, and we actually have most of what's in general purpose. The key that happened though, anybody who knows RTEMS knows we don't have ARINC, and it turns out that DDCI DIOS had a level A certified ARINC kernel with other capabilities that actually had no POSIX. So we had a chocolate and peanut butter moment and realized it looked like the right solution was to take 2 mature, robust operating systems, paravirtualize RTEMS, and then run RTEMS for the POSIX solution inside their unmodified kernel. The key is though, when I talk about this, there's 3 ways to view this. One is to say we're strictly focusing on FACE conformance, because we do plan to run it through FACE conformance. But you guys don't care about FACE conformance, that's just the reason we did this. The second reason is to focus on the path where you can start with a base RTEMS on a $5 board, run the same code on the POSIX services, and then move it into a protected and time and space partitioned environment, which actually is a meaningful thing to give you a real good path. It's exactly the same RTEMS that's moving along. Code is, for the APIs and services, is moving back and forth. So I wanted to do a little bit just to talk about what FACE. So there's 4 profiles, and they all look familiar. If you start with safety base as the middle, anybody ever worked on a system that only allocates objects, never allowed to free, and never exits? That's basically safety base type of system. The POSIX services are really cut down. Interesting, like general purpose, after general purpose, you don't have standard in and out, and error not allowed. And when you get to security, it's focused more on gateways. Each of these profiles is supposed to reflect operating systems and application uses of the services that have actually been through various types of like safety certification, like FAA certification, and various evaluations. So the DIOS 653 runtime actually satisfies the ARINC requirements for FACE. So they've got the required Part 1 services, and they have the required services from ARINC 653 Part 2, which are required under the FACE standard. One of the interesting things FACE does is it defines a subset of ARINC services which are supposed to be available to a POSIX application, which is sampling and queuing ports and the health calls in the safety and security profiles. So it defines a fairly normalized environment. Well, it isn't normalized, it's well defined. And there's a test suite that comes with, goes along with the standard, which allows you to test application code to ensure that it only follows the allowed APIs, and it ensures that the OS actually provides those APIs. So when we did the initial audit about a year ago, we realized we had 8 methods missing against the safety base. And the cool thing is, without knowing what's been happening, if you've been watching the RTEMS mailing list, these services have slowly been added. And hopefully this week, the mmap and shared memory code will go into the Git master. So we've added all of these APIs. POSIX dev control, the header file was added last week or week before last. And so far, by the end of the year or first week of January, we expect to have all the services actually available in the open version of RTEMS. And then it'll be a matter of just adapting the mmap to work in the virtualized environment. The interesting thing though is even though we're focused on safety base, if we look at the other profiles, at the moment, if you took RTEMS Git last week, you would have been missing POSIX dev control, which is actually not in the main POSIX standard. It's in an addendum with only 1 method. And the shared memory call is missing. And that should go in this week. Did the slide change? Yes, the slide changed. So you go to safety base. Interestingly, we're missing the same 2 calls because security is a proper subset of safety base. Safety extended, the main thing we're missing is that this is a multi-process standard, not a single process. So we pretty much meet it, but don't have the multiple processes. So, I mean, when you guys talk about using POSIX, you've got some subset which probably, truthfully, probably matches somewhere along in here without really formally verifying it. The general purpose profile, one of the things that's really interesting I find about the general purpose is that, for those of you who don't know, we use the same C library as SIGWIN. Well, all the methods in italics there are actually not, are things that should be in the math or C library but are not. But I looked at the math I've been tracking for a few years. They're also not in NetBSD. So there must really not be much code out there that uses them. Those are like, some of those I think are long double complex math, which I don't think is used a lot. So anyway, we have 90% of what's in, no, I'm sorry, we have, with the new network stack, we have 90% of what's in this. These profiles all have networking, which is different than the old POSIX profiles, the PSE 51 to 53, 54. So these were all designed for basically cockpit avionics, but they have generally, this looks like a normal standard. It's a POSIX profile on top of ARINC, and then the services on top of it look like CFS if we relabeled CFS. It's all message passing. So basically, when we started talking about this, RTEMS had POSIX, they had no ARINC, and they had the ARINC and no POSIX, but we both had a long history. They have 18 years of certification. DIOS came out of Honeywell, and then a number of years ago was spun off to DDCI. The original Honeywell team has followed it, and I can't believe it, but we've been around 27 years now, and the space history is long enough where I think at least one satellite I know of has reached end of life, and one has been deorbited, which was a milestone I don't know that I ever saw coming. Sometimes you look for milestones, and then sometimes they hit you. The deorbit was a long, you realize the mission has gone long enough to hit end of life, you've done something. This is another standard face picture. The idea here showing that the OS segment in FACE is composed of multiple classes of services. FACE even defines programming language subsets that are considered safe for embedded avionics use. So two of the components in there are their ARINC libraries for the ARINC services and RTEMS for the POSIX. We focused on the RTEMS POSIX, but all of RTEMS is really in there. We're only doing the FACE test, seeing what meets the FACE requirements. The classic API is in there. The dynamic library, libdl, is still in there. Every service is still in there. We just haven't mapped all of the device drivers down. We'll do that as people need them. So this is a high-level architecture picture of DIOS. Basically, the idea here is in the upper rows, you just see that you generally will put your application in one or more partitions, and you can use, they encourage you to do user mode device drivers, and then those can map to specific hardware, so you have very good control over that. The DIOS, interestingly, is built on a model of dynamic libraries, so there's binary reuse from system to system. The intention is that the RTEMS image will also be a compiled binary that can be used unmodified from system to system. This is a standard RTEMS figure, and basically the hardware is being replaced with a paravirtualization layer in this solution. The board support package is an adapter to DIOS, and the plan is we're not building in our TCP/IP stack. We're going to use theirs, which they have done certification work on, and the rest of the things just come along. And we've actually discussed using the RTEMS POSIX partition to run GNU Ada. So that it brings in a lot. So the overall solution looks like you're just running RTEMS in a partition, regular 653 code in another partition. They can communicate using shared memory or message sampling your queuing ports, and the DIOS kernel just swaps between them. So far on the integration challenges, RTEMS had already supported paravirtualization on some architectures. So what we had to do was basically just ensure that it was properly adapted to the DIOS kernel. So in fact, the DIOS kernel has not been modified in this. So since we didn't really change any code in RTEMS except the to change the protected mode supervisor instructions with the proper user instructions in this environment. Everything else compiles exactly the same. Mostly we've been working on the adapter and adding missing POSIX services so we can go through the face verification effort. So the cool thing is we both use GNU tools. One of the challenges was that we actually, RTEMS used a newer version of the GNU tools than DIOS did, and we had a newer version of Dwarf than they were used to using. So, but they updated, so we're all on very recent tools. They also use Eclipse, and they've got a number of plugins that are tailored toward their environment, integrated into it. And there's an RTEMS application builder that slowly is getting better as people make suggestions. But basically, you're going to start with a main in a POSIX environment as the default one. So far, there have been absolutely zero changes to DIOS, and all changes to RTEMS that affect anything common have been to add more services and to improve the paravirtualization adapter layer. And all of that actually is in the Git master. So this will all be in line with 4.12, which should release soon. So this is a pretty clean solution. So basically, interrupt, enable, and disable is replaced with calls in the paravirtualized BSP. We did find that actually the C library, for some reason, had some protected mode instructions in set jump, which I can't figure out why. They actually had been there so long that they predated the version control system, and no one had any recollection of why they were there. I have a vague recollection that I might have added them like in 92 or 93, but I can't prove that, and we know they're not necessary, so we just removed them. RTEMS has paravirtualized support for x86, PowerPC, and Spark. DIOS actually supports x86, PowerPC, ARM, and MIPS. So the ARM is the only one that will be next. The DIOS, so basically when you intersect us, the x86 and the PowerPC are there now. The ARM is the next one online. And the Spark I think requires work on the DIOS side. Our RTEMS Spark port already runs paravirtualized in a number of environments. So one of the things that we've had to discuss, and it's kind of interesting in the OS group, I don't know that we've actually walked through as much as we should, because you're on the OS group too, what it means to get POSIX behavior inside an A-Rink partition and maintain both schedulers so they look right. POSIX expects different things than A-Rink. So we think we've made decisions that keep the behavior the same as much as possible, because POSIX is very event-driven and allows you to have a very flexible, and A-Rink is a very rigid, manually laid out schedule. So there'll be, probably before this is done, there'll be two options. Right now, you just run to consume your entire time window, so that, and time advances at the beginning of each one of your time windows to make up. So you might not have ran for a second, but so all of your delays and time has to update to make sure you actually reflect what went on in the outside world. Because normally you would be completely virtualized away from time changing. So basically you're responsible for knowing to make sure the delays that would have passed while you were not the executing partition are honored. So this will be an issue. This is a challenge, but I think the solution's right. There are only two solutions, so we'll probably end up giving both as an integration option. So basically you just schedule your POSIX windows in with your A-Rink windows. DIOS has a number of scheduling options. They have a rate monotonic option. They have a Slack scheduler. They have a multi-core solution, so you can schedule your POSIX in parallel. You can because they're virtualized, you can mix criticality of applications if that works in your environment. So it's essentially a very flexible environment. Notice you can schedule your TCP/IP stack to run, and I've tried to go through this fast because it's got a lot of pieces and parts, and there should be questions. So basically, they've got certified A-Rink 653 with level A artifacts, and we've got a long history from the space and other communities. But putting them together lets you get the best of both worlds. So we are planning to submit to verification to get the certification, OS certification conformance, and I'm sure, like everything else in software, it's never really done right. We always keep working on it because we can always think of a better way to do it. And users tell you things that you could have thought of you should have thought of, but you never remember, right? The real world is different than what you think it is. So that's why RTEMS has so many options, is because you guys have told us how to make it better and tweak things. I think Alan has been responsible for a few personally over the years. So any questions? I'm holding everybody up for lunch. Is that the problem?
Operating system got us back on schedule. Thank you, sir. It's about, I don't know, about 11:45, so let's come back 1:45. We'll start then, okay? Does everybody know there's a sandwich shop just to the north? Caltech cafeteria to the east on the other side of the big Beckman dome kind of a thing. And if you get yourself over to Lake Street, which is about 2 blocks that way, there's more restaurants than, as they say in the vernacular, Carter has to do. Okay. Steve, if you have a moment, I'll load your stuff. Thank you. Sure. So you have your stuff right